From raw rock to reactor fuel, from ancient atoms to clean electricity, this is the dangerous, precise, and extraordinary journey of enriched uranium art. Today, we go inside one of the most complex and high-stakes processes ever created by humanity. Welcome to Factory Founder, where we uncover how the world's most powerful industries actually work.
Imagine a single atom, buried for billions of years beneath the Earth, holding the power to light entire cities or to destroy them. This is the story of enriched uranium, the invisible fuel that powers 1/5 of the world's clean electricity, yet begins its life in some of the most remote and hazardous places on Earth. From the first aerial survey to the final flicker of a light bulb, every step is a masterpiece of human engineering, precision, and risk. Core samples are drilled deep into the Earth, logged in makeshift labs, and analyzed in mobile trailers where spectrometers reveal the exact uranium concentration.
These pitchblende streaks are highly anomalous.
Agreed. The carnotite staining is also spiking.
The gamma readings confirm it. We're in a rich zone.
Documenting for the report?
This high-grade zone aligns with the latest drill logs.
Yes, but we need to confirm regulatory thresholds. The 3D model shows potential for expansion. Agreed. Let's review the timeline for compliance.
Every map, every data point, every cautious step is part of a high-stakes treasure hunt that will decide whether a mine is even worth opening. This is where the journey of enriched uranium begins, not with drama, but with patient, meticulous discovery.
Left side charge is set. Confirm continuity. Continuity green. Moving to arming sequence. Right side secure. Dosimeter level stable. All clear. Evacuate to safe zone. Copy that. Team 2 confirms. All clear. Detonation sequence initiated. Evacuate to safe zones. All right. Lower the bucket. Bucket's full. Swing it over. Dump it. Clear. Good load. Get the next one.
The raw ore arrives at the mill, a fortress of steel and concrete on the edge of the mine. Giant crushers and ball mills grind it to powder.
Hold steady, advancing the boom. Readings are stable, proceed. Watch the dust level, ventilation's lagging. Copy, slowing feed rate. Flow is stable. Column 1A is loading well. Confirmed. pH is optimal at 70 rising. Approaching target.
Good. Monitor for breakthrough.
Will do.
Ready for regeneration.
Conveyor rate is steady. Ore feed looks good. Copy. Ball mill rotation is optimal. Slurry density is rising. Watch for dust overload. Sprays are on. Sample from press 1 is flowing clear. Vacuum holding steady at 28 inches. Conveyor speed is optimal. Cakes are forming well.
In bubbling leaching tanks, sulfuric acid dissolves the uranium, separating it from worthless rock. Through solvent extraction and ion exchange columns, the uranium is purified, then precipitated into a bright yellow paste called ammonium diuranate. This is dried and calcined into the final product, uranium oxide concentrate, yellow cake. Workers in full protective suits fill steel drums under strict radiation control. What was once scattered rock is now a concentrated, transportable powder.
Starting the uranium assay on lot 24001.
Calibrating the ICP-OES now. Monitor is updating.
Sample prepared. Moving to the gamma counter, it meets the nuclear specifications.
Yellow cake travels to a heavily guarded conversion plant. Here, it is dissolved in nitric acid, purified, and chemically transformed through a dangerous dance of fluorine chemistry. First it becomes uranium trioxide, then green salt, UF4, and finally, in flame reactors using elemental fluorine, it is converted into uranium hexafluoride, UF6, a corrosive, toxic gas that sublimes at room temperature.
Uranium trioxide flow is steady. HF gas is reacting. Scrubber is active. Steam release is nominal. Green salt is collecting. Monitoring confirmed. Process is stable.
The entire process is conducted behind thick shielding and under relentless monitoring. One mistake with fluorine or hydrofluoric acid could be catastrophic. Yet every cylinder of UF6 that leaves this plant is a small miracle of industrial chemistry, carrying the raw material that will soon be enriched for the reactor core. Now comes the most technically breathtaking step. Inside cavernous, climate-controlled halls, thousands of gas centrifuges, each spinning at supersonic speeds, exploit a tiny difference in mass between uranium-235 and uranium-238. UF6 gas is fed into these spinning rotors. Centrifugal force pushes the heavier U-238 molecules outward, while the lighter U-235 concentrates near the center. Sophisticated cascades multiply this effect. Enriched UF6 returns to another secure facility where it is chemically deconverted back into uranium dioxide powder. This powder is pressed, sintered at 1,700 degrees Celsius, and ground into precise ceramic pellets. The pellets are loaded into zirconium alloy tubes, pressurized with helium and welded shut to form fuel rods. Hundreds of rods are then assembled into complete fuel bundles, the finished product that will sit inside a reactor for up to 7 years. Every pellet, every weld, every assembly is inspected with the rigor of a spacecraft component. What began as yellow powder has become high-tech nuclear fuel, ready to release its energy through controlled fission.
The grain boundaries are well defined.
Agreed. Density looks optimal. Check the cladding integrity.
Placing the pellet now.
Good. Porosity is low. This batch is
Log the results.
At the nuclear power plant, fresh fuel assemblies are lowered by massive cranes into the reactor core during carefully choreographed refueling outages. Once the vessel is sealed, the chain reaction begins. Neutrons split you. 2, 3, 5 atoms, releasing heat that turns water to steam, spins turbines, and generates electricity for millions of homes. Operators in the control room watch every parameter with quiet intensity. For years, the fuel burns, producing power with almost no carbon emissions. But as the uranium is consumed, fission products build up, and the fuel eventually becomes spent.
Initiating in-core scan. Detectors active. Neutron flux stable. Burn-up monitoring nominal. Coolant flow steady. All systems green.
Starting coolant sample analysis.
Monitors are ready. Trends look stable.
Transferring sample now. Precision is key. Confirmed. Gamma peaks ensures safety and control.
The spent fuel is moved underwater to cooling pools, glowing with eerie blue Cherenkov radiation. After years of cooling, it is sealed inside massive dry storage casks, steel and concrete fortresses that sit on concrete pads under constant security. In the long-term vision, these casks will eventually travel to deep geological repositories, where the waste will be entombed in stable rock formations hundreds of meters underground for tens of thousands of years. Whether the fuel cycle remains open or is closed through reprocessing, the final responsibility is the same: to isolate humanity's most potent waste from the living world forever. Yet the story does not end at the power plant. Enriched uranium powers far more than electricity. In hospitals, uranium targets in research reactors produce life-saving medical isotopes used in millions of cancer diagnoses and heart scans every year.
Pressure levels stable, core output is optimal. Confirmed, turbine response is excellent. Enriched uranium is delivering unlimited power for propulsion. All systems are green. She's ready.
Nuclear-powered submarines and aircraft carriers cruise the oceans for decades without refueling, thanks to highly enriched uranium cores.
Confirmed, no
In space,
anomalies.
compact uranium systems keep rovers and probes alive where solar power fails. Advanced reactors are now being designed to supply high-temperature process heat for hydrogen production, desalination, and even synthetic fuels, proving that enriched uranium is not only the fuel of electricity, but the key to a cleaner, more resilient industrial future.